we all should be familiar, if you have any experience with Abaqus, you recognize that there are two solvers that are the principal solvers for the Abaqus Unified Finite Element Analysis or Unified FEA program. And I want to point out that the 3D Experience platform uses the same exact solvers. So there is no solver base or code base for the 3D Experience platform and different code base for the Abaqus UFEA codes. They are the same codes. There's one solver, so for those of you moving to the 3D Experience platform, you're already going to be using the Abaqus solvers that you're familiar with. Beginning with Abaqus Standard, it's known as Abaqus Standard because it is the original solver that was developed starting with David Hibbett in the late 70s and was released for the first time in, I want to say, 1978. It's an implicit solver. It's an implicit solver. We're going to talk about the differences between implicit and explicit solutions in a moment, but just for now, recognize that there is a difference. It's an implicit solver for general nonlinear static and dynamic problems. Is also very effective for linear simulations such as linear dynamics and eigenvalue analysis and the like, and is also very effective for multiphysics. The second solver, second only in terms of chronology, is Abaqus Explicit, which is, as the name implies, an explicit solution technique. Was started in the late 1980s and was released in the early 1990s. It is an explicit solver for dynamic equilibrium, and was created simply to address those circumstances which are not well handled by an implicit solver. And what are some of those? Well, one of them is, here's an example of a highly dynamic simulation, and I want to take this opportunity also to acknowledge a colleague of ours, Randy Marlowe, who gave a similar presentation to this about two and a half years ago, and his presentation was a little bit more into the theory and high-level application of Abaqus Explicit. I'm going to get a little bit more into the application specific. And Randy, I borrowed very heavily from Randy's introductory slides in order to produce these. This was an example simulation that he showed during his presentation, for example. So if we're familiar with Abaqus Explicit, this is our standard copper rod impacting a oblique plate impact problem. Very highly dynamic, lots of changes of contact. But Abaqus Explicit is not just appropriate for some of these highly dynamic problems. It is also extremely helpful for some of these not quite as dynamic looking problems, like this extending of a wire, twisting it, and then allowing it to sort of collapse back upon itself. So this is not very highly dynamic. This is taking place over tenths of seconds rather than tenths of milliseconds, as is typical with highly dynamic applications. Notice also that the analysis has not been completed. Well, why is it we're seeing results even though the analysis was not completed? Well, we'll talk a little bit more about that in one of the advantages of Abaqus Explicit over Abaqus Standard, or one of the advantages of using it. So I've gone very high level of talking about implicit versus explicit time integration. These are the two principal methodologies that are used for solving time-dependent ordinary and partial differential equations. And as a mathematical example of looking at the implicit versus explicit methodologies, let's start by looking at the implicit methodology, whereby we are solving for the next state of the system, or the n+1 state of the system, by implying a solution at that state and then iterating on that implied solution until we get convergence. This is very different from an explicit methodology of time integration, whereby we are not implying a solution at the n+1 state, but we are explicitly solving for the solution at the n+1 state based on everything that we already know. So this is a nice mathematical way of looking at it, but I always find a practical example to be somewhat helpful. So think of it, you're driving your car. So you're driving your car down the road. In an explicit time integration scheme, you cannot see anything in front of you. You can only be driving while looking in the rearview mirror. So you know perfectly well everything that happened in the past. You know everything that's in your rearview mirror, but you're blackout on the front of you. So you have no idea what's in front of you. In an implicit scheme, that blackout shade is gone, but you have a lot of fog. And so as you're driving along, your perception of that solution gets a little bit better as you are converging closer and closer and closer to your end result. So it's the difference between driving through fog where you can still see ahead of you and driving along so that you're only looking in the rearview mirror. Now, as you might imagine, driving along when you're only looking in the rearview mirror, you must take very, very small increments as you're going forward. The explicit time integration scheme is what is known as conditionally stable. In other words, there's a chunk of time that you cannot exceed in order to advance forward and into a stable solution. That is not the case with implicit dynamics, whereby we have an unconditionally stable solution. So you can take very, very large chunks of time and go forward. So you might be asking why, okay, so before we ask that particular question, let's talk a little bit about the fact that Abaqus Standard and Abaqus Explicit from a dynamic perspective both solve the same dynamic equilibrium. And what Abaqus Explicit does is it takes advantage of the very computationally efficient solution technique of using lumped mass matrices in order to come to element level calculations that are extremely economical. And this is where the differentiation between an implicit and an explicit scheme takes place. Now, this is not unique to Abaqus Explicit. All the commercial and most of the non-commercial explicit dynamics FEA codes use this methodology because it makes the explicit methodology computationally beneficial. So in other words, you have to use a lot of time increments in order to get a stable solution using an explicit methodology, but those time increments are extremely small in computational cost. This is different, of course, from an implicit methodology where you must invert an entire system matrix and iterate until you get convergence on that implied solution. So Abaqus Explicit in particular and explicit methodologies, explicit dynamic methodologies in general, are designed to solve very highly discontinuous, high-speed dynamic problems, typically problems that have massive changes in the contact configuration between contacting bodies throughout the analysis. Generally speaking, Abaqus Explicit does not require as much storage or as much RAM as Abaqus Standard. Why? Because we're not storing large system matrices that have to be inverted and create very large matrices in and of themselves. This also helps aid in the computational efficiency of your explicit dynamics tool. Generally, it doesn't require as much disk space, although that's much less of a concern in this day and age where terabytes of disk space are readily available. As I mentioned earlier, we don't have to worry about the convergence of the Newton-Raphson method because we are solving for dynamic equilibrium explicitly, knowing only what we know in the past. We also find that Abaqus Explicit is very, very well suited for solving quasi-static problems, particularly problems that have very large deformations, static instabilities, and complex contact. Think, for example, of a metal forming operation where you're having metal flow or material flow that almost looks fluid-like through much of the simulation. You're getting very large deformations. There's very complex contact interactions. These problems are very well suited using Abaqus Explicit, so long as we do some things like maybe artificially speed up the loading rate or artificially mass scale so that we maintain a reasonable length of time for solution while maintaining our static nature of our problem. Abaqus Explicit also offers several unique solution frameworks that are not available in Abaqus Standard. One of them is the coupled Eulerian-Lagrangian solution framework. Typical finite elements, as we should know by now, are Lagrangian in nature. We are essentially printing a grid of integration points or elements onto a body and tracking the movement of those integration points and the transition of that mesh through space, through an ungridded, unbounded space. That is your typical Lagrangian methodology. Eulerian methodologies, as you can see here in my little cartoon, are more tracking of material through an undeforming grid. The CEL, or coupled Eulerian Lagrangian approach, is an alternative approach to traditional finite elements that allows us to solve very complex problems with very high degrees of deformation, like the Taylor-Anvil problem that most of us are familiar with. Another methodology that's available in Abaqus Explicit is the smoothed particle hydrodynamics, or SPH methodology. It's important to recognize that SPH is a continuum methodology. It is a continuum mechanics approach in that these particles, think of them as, if you think back to your basic formulation of finite element analysis, you take your grid of finite elements and then you determine Gauss integration points for each of those elements. Well, think of your SPH particles as being a particle surrounding each of those integration points. And you get an idea of how SPH, or smooth particle hydrodynamics, differs a little bit from traditional finite elements, but also how it's similar. It is still, in the end, a continuum mechanics approach because each of these individual particles are still related to each other through this kernel function. This kernel function does the job that the shape functions for traditional finite elements does. What smooth particle hydrodynamics allows us to do is to, again, solve very highly complex contact and impact sorts of problems, ballistics, modeling of explosives, etc. Very well handled with smooth particle hydrodynamics. Note again that this is a continuum mechanics approach, unlike the discrete element method. The discrete element method is similar to SPH. It's similar to smooth particle hydrodynamics in that it is a particle-based or a meshless method. The difference being that for the discrete element method, we're not treating these particles as if they're part of a continuum. We're treating these particles, think of them as if they were just rigid billiard balls stacked up on each other and are contacting each other elastically, or they can even have some stickiness and some inelasticity associated with the contact. What you're seeing on the picture on the right is one of the original authors of the discrete element method watching one of his pictures collapse into a heap of particles. So the difference between one of the things that DEM can model that is not well handled with SPH is, for example, aggregates or granular materials such as sand. Very well handled with DEM, not as well handled with SPH. So as part of all of these frameworks that are available in Abaqus Explicit, the question that you might be asking is, well, you know I have a dynamic problem to solve. Why would I use Abaqus Explicit over Abaqus Standard? Again, you have to come down to what is it you're trying to model. And for example, in Abaqus Explicit, there is a very comprehensive set, a library of materials that are available to you to solve these very complex problems, such as the pedaling and damage and fracture of metals, as we see in this double chamber aluminum cylinder experiment, which if you've taken the advanced explicit class, or even if you've taken the introduction to Abaqus class, you're probably familiar with this problem. Now, a lot of these materials are also available in Abaqus Standard, which aids in the transfer of data back and forth. And I'm going to talk a little bit more about the transfer of data back and forth between Abaqus Standard and Abaqus Explicit, so I'm not burying my lead here. So material damage is one of these examples of a complex phenomenon that is very effectively simulated simulated with Abaqus Explicit. And this is where we start to get into some of the updates that have happened within Abaqus Explicit over the last couple of years. For those of you who are in the life sciences industry, or for heaven forbid any of you who had to have a stent put in, you are already intimately familiar with super elastic plastic martensitic transforming solids. These are the materials that stents are made out of, among many other things that are made out of these materials, such as nitinol. These were available as built-in user subroutines in both Abaqus Standard and Abaqus Explicit. In Abaqus Standard, these were incorporated into the standard material library. With Abaqus Explicit, the general availability release of 2017, these became made available in Abaqus Explicit as well. So in both cases, this material model can effectively capture not only the super elastic plastic material, but also the shape memory functions for the materials as well. And with most, as is the case with most highly specific material models in Abaqus, we have specific output requests that are unique to those materials. Contact is one of the major challenges that Abaqus Explicit handles, frankly, better than most other tools that are out there. Explicit time integration is perfectly well suited for circumstances where contact surfaces are changing instantaneously to our eyes. Again, they don't physically happen instantaneously, but from our perception of what is happening, things that are happening on the microsecond level are not things that we are able, or most people are able to visually countenance. So when we are looking at Explicit, we are looking at a methodology where time steps are milliseconds or smaller, or tenths of milliseconds or smaller, that are tailor-made to handle the sorts of contact changes that are common when we're dealing with contact. And one of the major enhancements which happened in the 2018 general availability of release of Abaqus was not just the tracking of contact surfaces, but of the changes of contact edges. So we can now effectively model the crinkling of paper, which sounds facetious, and really who cares about the crinkling of paper, but it is a very, very challenging problem. Think of all of the components that are out there in the marketplace or out there in the world that have crumple zones. Crumple zones of automobiles, for example, the crumple zones of bumpers of trains. Very common in the transportation and mobility industry, but also extremely common in the industrial equipment and in the aerospace and defense industries. Think of the crumpling of material under a shock absorber or a crash absorption seat for a pilot seat for an airplane or a helicopter. The ability to effectively model these rapidly changing edge contact features is critically important to getting the correct answers, and to get the correct answers quickly and efficaciously. And as you can see, just going from Abaqus 2017 to Abaqus 2018, we get massive speed up in performance, and these have only continued to grow over the last couple of releases. The ability to model contact in axisymmetric and 2 dimensions, as a little blurb down the bottom, better than 60% of analyses, better than 60% of users at least occasionally use axisymmetric and 2D models, and the reasons for that are obvious. It basically, you do your early design analysis when you can do tens, hundreds, thousands, tens of thousands of trade-off studies, doing them in 2D space, so that you don't have to go through that expense in 3D. Greatly expands the design space, gives you more possibilities for robust design. And I crow about this one a little bit because I actually pushed for this enhancement for years in some of my previous assignments with the SOS system, and I'm thrilled. I was absolutely thrilled and continue to be thrilled that it was released in Abaqus 2018. It uses the same exact keywords and CAE interfaces that you're already familiar with from 3D general contact. is fully functional, robust, and does phenomenal for parallel scaling as well. So as I've been mentioning, Abaqus Explicit continues to evolve from the original hand-delivered to MIT code in 1992. Oh, for the days when we used to be able to put our code on floppy disks or even a handful of tapes. Again, as I mentioned earlier, the solvers between the 3D Experience platform and the Abaqus UFDA system are absolutely identical, and our enhancements continue to come from all phases of the simulation. We've highlighted a couple of them. I want to just highlight a couple more. As far as element technology, the usage of pyramid elements or the C3D5 element for mesh transition between hexahedral and tetrahedral meshes was made available with the general availability release of Abaqus 2018. These elements are unfortunately not available in Abaqus CAE. You can visualize them in Abaqus CAE, but Abaqus CAE's mesher will not create them for you automatically. So these are either elements that are going to come in from other codes, or I've known people who've written scripts to fill in the holes of some regions where these hex to tet transitions are necessary. Another major enhancement or major improvement was the addition of the C3D4H element, which had been available. This is a hybrid formulation element. Most people are familiar with the fact that tetrahedral elements in general, not specific to the Abaqus Explicit implementation, but in general, tend to be overly stiff. And so therefore they have they are problematic for scenarios where there is locking of the elements, of massive deformation and pileup of elements, as you're seeing, for example, here, the difference between the C3D4 for our copper rod or Taylor impact versus the C3D8R, which is a standard element which always compares very well as long as your mesh is adequate to tests. The C3D4H adds a little bit of additional cost because the hybrid formulation allows for pressure as an independent degree of freedom in the analysis, but smooths out all of the volumetric locking that is evidence in the C3D4 and gives you a very good computational result. Transferring data between Abaqus codes has been available for as long as Abaqus Standard and Abaqus Explicit have been available, and the transfers have always gone from one analysis into another. So from one Abaqus Standard into one Abaqus Explicit or vice versa. Beginning with the general availability of release of Abaqus 2018, this was enhanced to include multiple Abaqus Standard analyses or multiple Abaqus Explicit analyses into a single Abaqus Explicit analysis. Now, the workflow for this may or may not seem relatively obvious, but the one that comes to mind immediately is submodeling. So let's say you have a complex structure, you wanted to do static preload calculations in Abaqus Standard on multiple components of that model. Each team could, for example, deal with their own part of the system. All of those could then be combined and imported into a single Abaqus Explicit analysis. Now, what you might be asking is, well, what if I have some that's Abaqus Standard and some that's Abaqus Explicit? Unfortunately, the capability does not exist to mix multiple Abaqus Standard and Abaqus Explicit analyses into a single analysis. The workaround for that, however, is relatively straightforward. Take your Abaqus Standard models, put them into a single Abaqus Explicit analysis, and then take that explicit analysis and all of your other explicit analyses into a single Abaqus Explicit analysis. So that's a very simple, straightforward workaround for it, and therefore it's very, very powerful. We're going to talk a little bit about another technique to transfer data back and forth between codes that goes outside of the import capability. So again, when should I be using explicit? Short duration, highly dynamic applications. And if you are running Abaqus Standard analyses right now, chances are really, really good, unless you specifically have tokens where you told your sales rep, I am never going to run Abaqus Explicit, you have everything you need to run Abaqus Explicit. So let me talk a little bit about some recent customer papers to give you an idea of the breadth of usage of Abaqus Explicit. From our most current, our next ModSim or modeling simulation conference is coming up in October, so we don't have any papers from 2020 just yet, so 2019. And this is just a sampling of some of the papers. You'll notice some of them from the life sciences and consumer packaged goods industries. 2018, more consumers goods, architecture, engineering and construction, industrial equipment, high-tech, energy. 2017, aerospace and defense, life sciences. So what am I trying to tell you with this slide? What I'm trying to tell you with this slide is that Abaqus Explicit ain't just for cars and for planes and for things that go boom. It is very, very heavily used. And in fact, the life sciences industry and industrial equipment industries are really driving a lot of the changes that are happening and a lot of the enhancements and improvements in Abaqus Explicit that have been happening over the last couple of years. But we begin with crashworthiness. Crashworthiness is a great problem because it captures a lot of the things, a lot of the features that drive improvements in performance across the board. And we just love to crash our Toyota Venzas in these ludicrous looking, ridiculous circumstances. But they're important because these give us an indication of how well the code is performing. Crashworthiness simulations have to be faster and they have to be more accurate. These are being driven by our customers. They're telling us we need to be able to do these analyses very quickly. Our competitive pressures are pushing us to reduce design cycles. We have worked tirelessly over the years to improve the capability for handling large models. And the more we've handled the large models, including being able to do things like do realistic rendering, this looks like body in white or more like body in silver sort of models, but these look like what you would think an unpainted car that's been crashed into a bunch of other unpainted cars would look like. Gives you a very good sense for the design from looking at it. Hundreds of millions of equations, thousands of cores, very good scaling. So for our practical example, we look at crashing 8 of our Toyota Venza models, 229 million equations, 250 million equations in our code, and at 550 cores, the analysis runs in less than 18 hours. So you push the button on it at 5 o'clock at night, come back at 8 o'clock the next morning, your results will be waiting for you. Now, bear in mind, you're probably going to have terabytes of results, and that's just the way it is. That's the nature of the beast. A massive improvement with this year's general availability of release of Abaqus does what is known as hybrid message parallel or HMP processing, which combines the distributed memory parallel of MPI or message passing with the shared memory parallel or threads processing within the cores. And then so that shared memory parallel tends to be extremely fast and scale extremely well, but does not transfer well for cross connects between multiple nodes. That is what we use distributed memory parallel or message passing interface for. Combining these two can get you anywhere from a 10 to 40% improvement in performance, but the key here is not only do you get an improvement of performance, 25% for our 8-car Venza crash, but it also reduces the memory requirements overall because you are sharing memory within your compute nodes. And so therefore, we are now able to expand this problem to almost 500 million degrees of freedom, which will run on about 5,000 cores in a couple of days. So in a couple of days, you can do a realistic simulation of 14 cars crashing into each other. Another customer-driven enhancement was our customers coming to us and saying, look, we love that CEL is our coupled Eulerian Lagrangian is very effective at modeling the full deployment of airbags. But for the most part, once we have modeled the early deployment, we really don't care. We know it's going to work. Can you give us a methodology? Can you use this kinetic gas theory methodology that has been known about since the 40s to give us the early time solution of the problem? We listen to our customers, we listen to their needs, and we develop this LKM, which is this kinetic gas theory approach for solving the early time deployment of airbags. It works very well and is roughly half the cost of CEL. Of course, in order for airbags to deploy, you have to be able to pump mass, in this case the mass of gas or fluid, into the airbag. Hence we've incorporated inflator elements or inflators into our methodologies. All of these were available as keyword edits in the past, but as of last year, all of this methodology for developing inflators was made available as part of the Abaqus CAE GUI. So transferring data back and forth between codes can happen for import analyses. These are import analyses are a one-way coupled methodology. We are simply transferring data from one to another. As I'm sure most of you know, Abaqus has had a robust co-simulation capability between Abaqus Standard and Abaqus Explicit for many years. And in fact, that methodology was very quickly enhanced to include third-party tools so that we could do such problems as, for example, fluid structure interaction, structure electromagnetic interaction, and the like. The co-simulation methodology is think of it as a sequentially coupled simulation where the individual domains, be it fluid structure, for example, are solved independently, and then we are transferring interface loads at the boundaries. This is what makes it an explicit fashion. We are transferring the actually calculated loads at the boundaries and then moving on to the next time step. And one of the improvements, or one of the more recent enhancements, is our ability to co-simulate between Abaqus Explicit and our lattice-Boltzmann-based CFD solver known as XFlow, which is a relatively recent acquisition by Dassault Systèmes. One of the wonderful advantages of XFlow, and in addition to it being a phenomenal CFD solver, is that for those of us who are familiar with structural mechanics, the setup of these problems is extremely easy. So a colleague of mine, Asghar Yapar, presented at the 2018 Shock and Vibration Symposium this simulation of launching a mortar round. And you can look at the model that we've used in Abaqus Explicit for the mortar tube, and you're saying to yourself, this is ludicrously simple. But you'll notice that in spite of the fact that the model is very simple, we get extremely accurate prediction of the muzzle velocity for this projectile. And this methodology has now been employed at many customers around the world. The interface, the co-simulation interface between Abaqus Explicit and XFlow has now been standardized and formalized and is now available as general purpose. And people are just raving about how well it works. This was also presented, Asghar, Dr. Yapar presented this at the 2019 Shock and Vibration Symposium by doing an underwater explosion or undex attack on a submersible structure, and was phenomenally well received. So changing gears completely, getting out of sort of our core, what people think of for crash and for things that go boom, let's talk about a practical problem. How many of us have dropped their phones? I know it happens far more often than I like, which is why I have an OtterBox on my phone, right? Very common, but it's not just common for the high-tech industry. Every industry has to deal with the effects of people dropping things. Anybody who is designing anything that humans are going to interact with, they're going to drop them. So what do we want? We want robust designs. We want to not only survive the drop, but we want to be able to survive multiple drops because we're all Butterfingers. We need to be able to reduce the costs associated with physical tests. We want to speed up the development cycles, all the reasons that we do simulation in the first place. And now we're starting to see this moving into these non-traditional industries like high tech and consumer goods. They have some unique challenges. Talk about intellectual property control. The design of a new high-tech device is extremely sensitive to intellectual property, to the point that companies limit the availability of the full design to a very small select group of people. So you have these very complex devices with lots of components packed into tight spaces, and the people on the various teams are not allowed to talk to each other. They're not allowed to see how well their components fit together. So being able to do all of this with handling the multitude of scenarios, I mean, just think of all the different ways you drop a phone. Being able to handle all of those scenarios in an environment where intellectual property is absolutely vital to your survival as a business, well, the good news is the 3D Experience platform is tailor-made for exactly this sort of work. And in fact, a company that you may have heard of has already several years ago at the 2017 Science in the Age of Experience conference demonstrated how they were able to use this methodology to improve their prediction capabilities and make better designs. We have another public reference for this for field failure rates for mobile devices that goes all the way back to the 2011 Simulia Customer Conference. We don't even call it the Simulia Customer Conference anymore. Demonstrating that none of this is new. I mean, none of this is new, but it's now just recently coming to the forefront. And I want to close with a really interesting example of doing virtual drop test of a very complex device, another very complex high-tech device. You'll see in a second the very tight clearances that are associated with the multiple components of this camera. Won't say what brand it is. And in a second or two, you're going to see one of the more wonderful things about the Abaqus Explicit's ability to capture the response from the simulation. We hit again, and then we rebound, and in just a second, we're going to hit a third time. So we are able, with Abaqus Explicit, to effectively capture the very complex impact of this very complex device easily, simply. What our customers report to us is that Abaqus Explicit just works. It just works out of the box for these sorts of problems. And we hope that we have every reason to believe that that's going to continue, because we're going to keep developing our tool so that it works that way. So I hope this talk has been enough to whet your appetite and get you a little bit more interested in Abaqus Explicit and its capabilities and how it's evolved over the years. If you are interested in learning more about Abaqus Explicit, I cannot more highly recommend the Abaqus Explicit Advanced Topics class. I just taught it a couple of weeks ago to a private customer over GoToMeeting or GoToTraining. We are still very actively doing training, although not so much in person anymore. The Modeling Extreme Deformation and Fluid Flow class is for people who want to learn more about our CEL and SPH capabilities. If you're going to be crashing things, or really if you're going to be talking about impact in general, our Crashworthiness class is a great class for you to think about. For those of you who are transitioning to the 3D Experience platform or want to learn how to do more simulations on the 3D Experience platform, the Mechanical Scenario Creation Essentials class will give you an overview of how to employ Abaqus Explicit solver technology on the 3D Experience platform. And for learning all of these wonderful new capabilities for high performance visualization that are available to you on the 3D Experience platform, the Physics Results Explorer Essentials class. It's a one-day class. It's well worth your 8 hours to do it. As always, online help is available for our established products, Abaqus, iSight, etc., as well as online help being available for simulation on the 3D experience, both on-premise and cloud platforms.